couple of things. I want to go ahead and let you know what's happening. So we finished up with piecewise functions. We did our little activity last week, and I just mentioned if you still have a copy of that, or if you need another copy of that, right over here by Marcus in the filing system, there are extra copies, or if you can't find it, just let me know. If you've already turned it in, it's been graded. If not, just try to get that in as soon as possible. Here in the morning, just come on in, let me know. Now, this Thursday, we're going to have a quiz on rational functions. In fact, it's over this lesson right here. So we should be able to go ahead and get everything taken care of and go ahead and take our quiz. We'll see how that works out. But that's coming up on Thursday. Did I mention I won't be here Friday? I don't remember if I did or not. Okay, so on Friday, I have a professional development workshop I have to go to. I believe it's over college readiness. So I'm going to leave the assignment that you would have normally been given for this on that day. So you'll have the entire class period. You guys can work together, but it'll be due on Tuesday the 11th. And in fact, I'll go ahead and remind you of that, in the coming days. And we'll probably go ahead and do something different on the quiz because you won't have yet had time to practice on that. So, I got you covered. Don't worry about that. But quiz on Thursday, the homework you'll get on Friday when I'm not here. It'll be due on Tuesday. I just got a text message, so we'll ignore that for a second. The other big one coming up on Monday the 17th. Monday the 17th. So basically the next Monday we actually have school. That's going to be your second exam. All right, so anything, from the last exam on forward, we'll have rational functions, compositions, inverses, all that good stuff. But just like the previous one, I'll go ahead and let you guys use your notes. I think that went pretty well. I don't remember exactly what your average was, but I want to say it was in the 80s. So it turned out really well. I'm going to stop early today to pass back your papers so you can take a look at your test. And speaking of, I don't know that anybody in here still needs to take it, possibly. Actually, Nathaniel, yes. Nathaniel still needs to take his test. If I can get you to take this out in the hallway, sir. Okay, appreciate that. But I'll go ahead and pass back your papers. If you happen to have failed it, and I think there's only a few people who did, calculators are right over there if you want one, sir. You have until Tuesday morning the 11th, by the end of tutorials, 8:05. So if you want to come in during the morning, retake it, or if you want to get together with me, let me know, hey, I'll be coming after school, I want to retake. I'll set aside that time. I think, unless anybody has any questions, that's all I got. How's everybody? Good? Good? Okay, ready for a week of pre-cal?
Of course.
Yay! Andrea looks so stoked. Okay, let's get to it. All right, so rational function. So this is going to...
There's our two people right here.
All I've got are two chairs. Sorry, sir.
Calculator right here?
Sure. There you go. All right. So let's see. So this lesson here is pretty much going to bring everything together that I want to go ahead and make sure you know about rational functions. So we'll go ahead and start with the parent very quickly. This is the one that started it all. Okay, f of x is equal to 1 over x. Okay, does that parent look familiar? Okay, well, he has two branches, but more important, he has something that not every parent is going to have, what we call asymptotes. So let me go ahead and give you a quick sketch here. So the parent always starts with the horizontal asymptote on the x-axis and the vertical on the y-axis. So basically your axes are the original asymptotes. Does anybody know what quadrants my branches are going to be in? Those curved parts of the graph? Okay. Now, do you remember how the quadrants are numbered? There we go. It goes counterclockwise. So it goes 1, 2, 3, and 4. Okay. So what two quadrants will have this parent? 1 and 3, absolutely. Okay. So there we go. If you go ahead and put in some points, you're going to notice this is what we get. The domain is all reals except x can't equal 0 because we can't divide by 0. And the range is all reals except 0 as well, because that's where the asymptotes start. So these are the graphs I want to go ahead and practice and start getting you to think about as we go through. And they're going to get a little more complicated than that, but that's okay. We'll handle this one step at a time, and I think you'll be just fine. All right, so let's go ahead and fill in, and we'll just build up to everything we need. So it says, let n of x, the numerator, and d of x, the denominator, be polynomial functions where d of x can't equal 0. Then a rational function is, and because it's, let's just use r of x for rational. R of x would equal n of x divided by d of x. And you see why we have the restriction that d of x can't be 0, because we can't divide by 0. So basically, you've got some kind of polynomial divided by another polynomial. And we want to just investigate it. We want to get some information about it. Okay. Now, the domain of x includes all reals. These graphs are always infinitely wide. They're always going to go from negative to positive infinity. But typically, there are values that we have to throw out for one reason or another, except the values that cause, and I've actually already mentioned it several times today. Okay, Angel says division by 0, and he is correct. Division, whoa, that was weird. Division by 0. There we go. Cannot divide by 0. So any value of x that makes the denominator 0, we have to throw those out. They're going to be very useful in helping me write the domain. Now it says domain restrictions come from the values that make the, and I just said it. What do we call the expression in the bottom? The denominator that make the denominator 0. Squeak, squeak, squeak. Okay. All right. So why don't we go ahead and get straight to it. Now, I've put a little FYI right here. It says vertical asymptotes are the domain restrictions. So you can always say that your domain is all reals. But then you probably want to go ahead and add on except what are the values of x that make the denominator 0. So let's find the domain for this guy right here. X plus 7 over x squared minus 3x plus 2. So we're going to build up to this. Okay, we're going to talk about, the vertical asymptotes. We'll talk about the end behavior and all that good stuff. All right. So let's see. I need to go ahead and take this guy right here, x squared minus 3x plus 2. And I want to set him equal to 0, because any value of x that makes that a true statement, okay, he's got to be thrown out of my domain. He's those excluded values that I was referring to. So probably the number one method for finding these is to factor. Okay, but besides factoring, what are some other ways that we could solve a quadratic equation? What's that, sir? Completing the square. Perfect. That's a great way of doing it. And there's also a formula. Quadratic formula. Okay, so any of those could be used. If you have a preference, please go ahead and use it. Okay, as long as you're able to find those values. What would you like to do here? Just factor it? Okay. Now, factoring is usually one of the fastest and most efficient ways. So this is a simple trinomial because it starts with 1x squared. So I need two numbers that'll multiply to give me 2, but then turn around and give me negative 3. Now, let's think about this. What are the only factors of 2? Yeah, it's just 2 and 1, right? So I know that 1 times 2 will give me 2, but these two values have to add to give me a negative. So they both have to be negative. And that still works because what's a negative times a negative? See, it's still a positive. And now x times x will give me x squared. Probably on some Friday or sometime when I have a little bit more time in class, there's a method that I like to use for factoring trinomials. It's universal, doesn't matter what it is. If it's factorable, it's going to break it apart. And I always like to use it and I show everybody, but we'll get there. I'm not going to bother showing you today. But does anybody remember what's called the zero product property? Does that sound familiar? Okay. If not, here's what it says. The zero product property. Zero product property. Okay. It basically says if you have an expression where a times b is equal to 0. Okay. then you have basically a couple of cases. If you multiply two items and you get 0, then either A is equal to 0, or what do you think the other part is? B is equal to 0. As long as one of them is 0, you're going to get 0 when you multiply. That's the zero product property. So we're saying when we multiply these two groups, we should be getting 0. Okay, well that means that either the first group equals 0 or the second group equals 0. Okay, so it doesn't matter what happens in one group. If the other group goes to 0, the whole thing gets wiped out. Okay, so how would I solve this? What am I going to do with minus 1? Add 1 over. Okay, so plus 1, x equals 1. Then we'll go ahead and add 2. Okay, so there we go. And now this is what I'm referring to. They won't both become 0 at the same time, but let's say the 2, for instance. If I were to plug the 2 back in for both these x's, okay, 2 minus 1 times 2 minus 2. See, it doesn't matter that 2 minus 1, I'm still getting a number, right? The one group is what? 0, so the whole thing is 0. And the same thing would happen if you were to plug in 1. Okay, these are the values that make it true. Okay, so 1 and 2 make the denominator 0. And in fact, does anybody want me to plug it back into x squared minus 3x plus 2 just to show you that you're going to get 0? You want to see that? Okay, sure. So let's say x squared minus 3x. No. X squared minus 3x plus 2. Let's start with 1. So 1 squared minus 3 times 1 plus 2. Well, that's going to give me 1 minus 3 plus 2, which is what? Which is 0. Okay. Any value that makes the denominator 0, we call that a discontinuity. Now, we're probably not going to get very specific in here. Typically, they're going to be vertical asymptotes. Okay? And we could do the same thing if I plugged in 2. So that would be 2 squared minus 3 times 2 plus 2. So 2 squared? 4 minus 3 times 2? 6 plus 2. And that would also give me 0. Because 4 minus 6 plus 2 does all cancel. Okay. That's what we're looking for. So these values that I've thrown out, I can use any value of x except those two that I got. So there's a couple of ways I could say this. I could say all reals, but then I'd have to say except x cannot equal 1 or 2. Let me go ahead and take that off right there. So that would be a perfect way to go ahead and state your domain. Or some people like to go ahead and put it in your interval notation. This would be the exact same thing. So negative infinity to 1. And then we've got to go from 1 to 2. And then we got to go from 2 to infinity. And what do you do if you have more than one interval? How do you connect them? The union. There you go. So see, I want you to realize that this is saying the exact same thing that the previous is saying. And we know that 1 and 2 aren't part of it because we're using parentheses, not brackets. So the negative to positive infinity, that's the all reals portion. Okay, how we doing? Any questions? Yeah? Well, okay. Let's see what the bottom of the page has to tell us. So now let's focus on vertical and horizontal asymptotes. So vertical asymptotes are going to look like this. That's the equation of a vertical line. It's just x equals. So A represents any value of x that makes the denominator 0, just like we found 1 and 2. Okay? So on that previous graph, x equals 1 and x equals 2 would be your vertical asymptotes. And I want to make sure, I don't remember what the numerator was. X plus 7, yes, so there's no hole. Okay. Don't want anybody to be watching this later. I mean, hey, there was a hole on that rational function. Hey. Because I'm sure people do that, right? How many people have already gone home and just binge watched these videos? So many hands going up. I wish people at home could see that. All they have to do is go, just believe my auditory voice and they'll right, Linda Bell? Yes. Okay. Let's continue. So the graph behavior will approach the vertical line and either increase or decrease without bound. That is, and this is how we write it in pre-calculus. See, x approaches, that's what the little arrow means. And maybe I need to write this out. So the arrow means approaches. Okay. Does anybody know what LIM is short for? Limes in Mexico? Interesting. Not quite. Alison?
It's something with like
Lemonade?
limited.
Oh, limited. I thought you said lemonade as well. I was like, we like our lemons. But there you go. Yes. LIM is short for limit. It's a value that we approach, but we may never touch. Okay, so this is how it's read. The limit as x approaches a value. Now, when you have as a power a negative or a positive, that tells you what direction you're going to approach that asymptote from. So if it's negative, what direction is it? The left. Okay. So if it's a positive, what do you think it's going to be? From the right. Okay. So this is how these are read. The limit as x approaches a, some number from the left, or the limit as x approaches some value a from the right. Now, if you know you're looking at a vertical asymptote, which the majority of the time you will be, well, there's only two possibilities. You're either going to have a positive or a negative infinity. It's got to be one of the two. When they get close to that asymptote, the graph, they only have one of two choices. They either want to curve upward forever or they want to curve downward forever. Okay? So let's take a look at this guy over here. You'll notice we're curving up and we're curving down very close to what value? If I were to put a vertical asymptote in there, I would say it's -3. Who said it? Perfect. I would say that asymptote is at -3. See, that's what these graphs want to do. From the left or the right side, they have a choice to make. Either they're going to curve up or they're going to go ahead and curve down. Now, because my vertical asymptote is at -3, let's go ahead and write these using that notation. So for this first one, I'd say the limit as x approaches -3 from the left. See, where a power, an exponent would be, if you put a plus or a minus, that's the direction you're approaching that value. Okay, of f of x equals, well, let's see, on the left, okay, if I'm approaching it from the left side, what did the graph decide to do? Did he curve up or did he curve down? On the left side, he curved up. So this would be positive infinity. Okay, when you're talking about the vertical asymptotes, these are the only two possibilities, either positive or negative infinity. Now let's write it out for the right side. So this would be the limit as x approaches -3 from the right of f of x. So if I'm approaching it from the right side, what that graph want to do? He curved down. So he's going to keep going down forever. So he's negative infinity. Okay. Is this making sense? Okay. Do you want me to construct another one so we can practice writing it out? Or we feel we're comfortable with that? Good. Okay, good. Good. Now, horizontal asymptotes. Oop, let me use the eraser. That might help. Okay. Now I'm going to go ahead and put the vertical back in. X equals -3. Okay, so vertical asymptotes are going to have the form, x equals, that's a vertical line. Horizontal lines are going to be of the form y equals. And again, it's just some number that we'll go ahead and call b. Okay, we're just using a different variable because we're not saying it's always going to be the same as a vertical asymptote. Okay. So just like I put a vertical asymptote here, where would a horizontal asymptote fit so it looks like the branches are almost hugging it? Okay, say again, sir? 1. That's exactly right. There we go. Y equals 1. So straight up and down is x equals, straight left and right is the y equals. Okay. Now, the graph will tend toward, okay, plus or minus infinity along the line. Okay, it is possible to cross a horizontal asymptote. I'm going to show you about that. Probably not today, but definitely in the coming days. So here's my expression again, but it says the limit as x approaches what? Negative infinity. So this is your left and your right end behavior. This is the left side of the graph. Left side of the graph. So what do you think it means, limit as x approaches positive infinity? That's the right side. The right side of the graph. Okay. That's the right side of the graph. So you know you're dealing with a vertical asymptote because your statement is approaching a specific number from both sides. Just like here, say we were approaching -3 from the left and -3 from the right. But if your statement says we're approaching negative or positive infinity, you're interested, well, what's the graph doing as it pushes out along the x-axis? As x gets larger and larger, well, what's it getting closer to? And the same thing on the other side. If x is getting smaller and smaller and smaller, the graph is going to again curve towards a specific number. Okay? And in this case here, anybody think they want to go ahead and tell me what it is? The limit as x approaches negative infinity of f of x. Remember, what was the value of the horizontal asymptote you told me? This was y equals 1, right? So as x gets smaller and smaller, this guy's going to curve down, and he's going to get closer and closer to 1. Now, he's going to approach 1 from above, but that's okay. He's still going to get as close to 1 as he can. Well, look at the other side. This time just says infinity, so what direction do I go? I'm going right. Now, maybe the graph curves up, maybe it curves down, but as I'm going to the right, that branch, he's again curving towards what? There you go. On the outer ends, those end behaviors, okay, the graph is going to approach that horizontal asymptote, whatever it may be. So in this case, he's approaching 1 as well. Now see, they may be approaching it from different directions. The one on the left is approaching it from above. The one on the right is approaching it from below. And that doesn't matter. That doesn't make a difference. Okay? You're still getting closer and closer to 1 without actually hitting it. Okay? Do you guys want me to draw another one? Just so you feel comfortable with these? Sure? Okay. Let me go ahead and just make one up. Okay. So let's say I've got, let's say this one. So this is x equals, let's say 4. And then we have y equals -2. Okay, so you can very clearly see, you know, a vertical and a horizontal asymptote, right? And let's say this is what my branches look like. It's going to curve like this, and maybe he curves like this. Okay. So given this graph, I'd want you to answer 4 questions. Okay. So the limit as x approaches 4 from the left, the limit as x approaches 4 from the right. So this is what's going to be happening around the asymptote. What are the other 2 statements going to say? As x approaches what? Positive and negative infinity. So we'll also have the limit as x approaches negative infinity of f of x, and we'll have the limit as x approaches positive infinity of f of x. Now remember, when it's approaching negative or positive infinity, those are the extreme ends of your graph, the far left and the far right. Okay, when it's approaching a specific number, odds are that's going to be a vertical asymptote. Okay, so let's see. I'm approaching 4 from the left. Okay, Well, what did the graph want to do? What's it doing on the left side? Did it curve up or did it curve down? Yeah, on the left side, I've got this guy, and you'll notice the closer we get to 4, he's choosing to go down, right? So what would I put here? Negative infinity. Okay. But on the right side, as I approach 4 from the right, I'm moving along the graph right here. He decides to do what? He's going up to positive infinity. Okay. Now remember, if you're approaching a specific number, okay, that's an asymptote, a vertical asymptote, then it's going to be positive or negative infinity. Can anybody tell me the limit as x approaches negative infinity? So if I'm on this branch right here, and I just want to start going out, I'm going to keep going forever and ever. Christian? He says negative 2, because isn't that my horizontal asymptote? Okay. Well, what if in the other direction? I get on this guy and I just start riding the graph all the way. X just keeps increasing without bound. What's he want to get close to? Negative 2. That's it. That's all there is to it. Anybody confused by this? By not seeing where I'm getting my values? We're good? Okay. All right. Now, we talked about those vertical asymptotes. Those are the values of x that make the denominator 0. Okay. But now, how are we going to know where the horizontal asymptotes are? Well, I'm glad you asked. That's a very good question. Let's take a look at our 3 cases. All right. Case number 1. The numerator degree is less than the denominator's degree. Okay, so first I'll back up. What are we talking about when we say degree? The largest power. Okay, the largest power that any term has. So you want to look for the degree of the numerator and the denominator. Okay. All right. So the degree is the highest power. Okay. Now, what you're going to do, it says the line y equals 0 is the horizontal asymptote. This is if the degree of the numerator is less than the degree of the denominator. So let's say you have an expression, f of x is equal to maybe x plus 1 divided by x squared plus 3x minus 2. Okay. What's the degree of the numerator? It's 1. In the numerator, the largest power we have is 1, right? Now look at the denominator separately. What's the largest power you have there? It's 2. So those are what we're referring to when we say degrees. Okay. If the denominator's degree is larger, you don't have to do any work. Automatically, it's y equals 0. Remember, that's just the x-axis. Okay. Now, here's case number 2. What if the numerator degree is equal to the denominator's degree? What if they're the same? Well, the ratio of the leading coefficients, is the horizontal asymptote. So you take that leading coefficient divided by that one. So let's say I were to have something like this. F of x equals, let's say 8x squared plus 2x minus 1. I'm just completely making this up. Divided by 2x squared plus 5x plus 7. Let's say you have some rational function like that. Okay. Well, look at your degrees. What's the degree of the numerator? 2. The degree of the denominator? 2. If the degrees are the same, then you simply divide the leading coefficients. Now, the leading coefficients are the terms that give you the largest power. So here it would be 8 and 2. Those are the coefficients of the terms with the largest power. And this is what the A over B refers to. So this guy would have a horizontal asymptote at y equals 8 divided by 2, which we know is what? 4. So he'd have a horizontal asymptote at 4. Okay. Now, the only thing, I've got another one on my paper, and this is really easy to do, but let's say this isn't for the third case. I just don't have enough room just yet. Let's say you were given one like this, okay, kind of a variation of this one. Let's say f of x is equal to 5 minus 8x squared over 2x squared plus 3x minus 4. Okay. What did they do in the numerator? They switched the order of the terms. Okay, so you want to be careful about that. Sometimes they're going to get tricky and switch these around just to see if they can catch you. I mean, 5 minus 8x squared, isn't that the same as negative 8x squared plus 5? See, I kept the same sign, I just reversed them back. Okay, so you just want to be sure you're dividing the correct numbers. So now I should be dividing negative 8 by 2, not the 5 divided by 2. It's the coefficient of the term that has that largest power. Okay. How much of this is kind of coming back from Algebra 2? Do you guys remember this? Good, 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 good. Okay. Well, let's look at this last one here. What if the numerator's degree is greater than the denominator's degree? Does anybody remember? This is a special case. There's no horizontal, but there is a what? Not a vertical. Now, this has no bearing on whether there's a vertical or not. This is just looking at the horizontal. Now, in this case, there's not going to be a horizontal, but you will have a slant asymptote. And, you know, in mathematics, we always have fancy words to describe things. So if you ever see that word oblique, oblique is just what we use for a slant asymptote. Okay. I know you're probably thinking, wow, at this point, man, this lesson's starting to look pretty oblique, but okay. It's been 3 days. You'll laugh later. Okay. But anyways, a slant asymptote. Now, let me give you an example. Let's say f of x equals x squared minus 5x plus 4, x squared minus 5x plus 4, and I want to divide that by x minus 2. Okay. Well, again, go ahead and take a look at your degrees. The one that's going to happen most often for us is going to be that the numerators and the denominators have the same degree. I might go ahead and throw in a few of the others just to make sure you're aware of that, but the degree of the numerator here is 2, while that one has a degree of 1. So if this is the case, if I want to know where my oblique, my slant asymptote is, we have to use division. Okay. Now, I'll go ahead and let you guys decide. We either have long division, or do any of you remember synthetic division? Okay. Genevieve? Yes. Okay. Now, I would probably recommend synthetic division just because it's a lot faster. You don't have near as much work. I can show you both ways if you like, and you can decide whichever way is better for you. Let's start with the synthetic. So for synthetic, you got to put a half box in the top left corner, and you're going to draw a little line right below it. Okay, this is your framework, like your setup. Okay. Now, you see the coefficients of your dividend? You have 1, -5, and 4. Those are what's going to go outside the box to the right. Now, if it's being subtracted, you want to make sure to keep it negative. So I'm going to say 1, -5, and 4. Okay. You always put them in order of your powers decreasing. That's what we call standard form. Okay. Now, does anybody remember if a term is missing? What if it had gone straight from x squared and then just said plus 4? You got to put a 0. You always have to put a placeholder for a missing term. That's very good. Does anybody know what's going to go right here? A positive 2. Whatever your constant is, you always put the opposite of that value. Or think of it like this. What's the value that would make that expression 0? Okay. Now, does anybody remember what we do above the line? If we're above the line, we add. If we're below the line, we multiply. Let me go ahead and move this plus over a little bit. Beep. Oh, that didn't work. Oh, that's still off from the other one. There, we don't need you. Okay. So I'm going to go ahead and say plus. Now, here's how you do it. The first number in that box always drops no matter what. So you're always going to start with multiplication, and then you just alternate. You multiply, add, until the whole thing is filled in. Okay. So what is 2 times 1? 2. I'm going to put that 2 right there. And see, now that I'm above the line, I add. So 1 plus 2, 3. I'm going to put the 3 right below it. Okay. And now I start again. 3 times 2, because you always multiply by what's in the box. 6. Negative 5 plus 6, 1. And then 2 times 1, 2. And then 4 plus 2, 6. Okay. Now, whatever is here, that's your remainder. Okay. And remember when you did long division way back in the day, you take the remainder and you put it over the divisor? Okay. Here, I'm not really too concerned with that. I'm really just interested in you guys getting me the slant asymptote. Does anybody know what I'm going to do with the 2, 3, and the 1? Okay. What's that? How's that? No? Lilibel? Was it Lilibel? What'd you say?
I'm going to do it like in the X.
There you go. This is going to give you your answer. This is your quotient right here, the 2, 3, and the 1, and that 6 remainder. Whatever degree your dividend starts with, you always start yours 1 degree less. So this one started x squared, so I'd start that one with x. Okay. Then you have your constant and, whatever's left. Does that make sense? Okay. Hold on. Drop 2. Yeah, the first one drops. I'm pretty sure. All right, I may or may not have made a mistake on that. I'm going to go back and look at it, but right now, let's focus on it. And if I did make a mistake, I'll come back tomorrow and definitely own up to it. But let's, for right now, 2x plus 3. Now, the rest of it, there is notation in calculus for showing how it goes to infinity and how those just disappear. Once you have the linear function, because it's just a straight line, that's all we need. Okay. So 2x plus 3, that's your slant asymptote. Okay. Do you guys remember that? Remember doing that? Okay. Maybe I can make some of those into focus activities just to get a little more practice or something? Okay. All right. Cool. All right. Well, let's see. I got 12:31. Well, let's at least go ahead and get started. It will become important as we move through our course to be able to analyze functions completely without access to a graphing utility. Okay, and this is actually what's going to happen on Thursday when we look at our quiz and on our homework. We want to be able to do this without the calculator, and that's fine. We can do this. You should begin to develop some procedural thinking to help you along this pathway. So here's all we want to go ahead and find, right? So here's my function. Okay. So this one is already given to me factored. So maybe in order to answer some of these questions, we'll go ahead and write it out. So I'm going to go ahead and put the 2 here. How do I multiply these together again? What's that acronym? You wrap leftovers in it occasionally? FOIL. What does FOIL stand for? First, outside, inside, last. It's just a set of instructions that tells you how to multiply 2 binomials. Okay. So I'm going to multiply the first. So x times x will give me x squared. Now we're going to go outside. So what's x times 3? Plus 3x. Now I'm going to go inside. Negative 2 times x is minus 2x. And then I'm going to multiply the last. Minus 6. All right. So 3x minus 2x. That's just x. So x squared plus x minus 6. Okay. Now you can also do this. If your numerator, and this one's kind of a unique case, if your numerator doesn't have an x, maybe it would help you, because we're looking at the degrees, to just put x to the 0 up there. Because you guys remember from your exponent rules, what's anything to the 0 power? It's just 1, yeah. So that is equivalent, right? Because that's really 2 times 1, it's just 2. But maybe this will help you out when you're looking. So let this be our last question, and we'll go ahead and stop here today. I know, I'm sad too. What would be happening here? Would there be a horizontal or a slant asymptote? Look at our degrees. Definitely horizontal. Now, would it be y equals 0, or would I divide the leading coefficients? Okay, I'm hearing a couple people tell me it's going to be y equals 0. This is the first case. The numerator's degree is less than the denominator's degree. Okay. So I immediately know I have a horizontal asymptote, y equals 0. There you go. Okay, so we'll go ahead and stop there. Thank you so much, guys. You did another great job today. I appreciate it. Okay.